All right, welcome to lesson 5-7. Today we're going to continue working on some different methods for integration. Specifically today we're looking at integration and logarithmic functions. So to lead into it, let's start by looking at this, what appears to be a basic integral. And that would be the integral of 1 over x dx. So based on everything you've learned up to this point, I would expect that some of you are thinking to rewrite this as x to the negative first dx, and you would be correct in terms of that being your first instinct. And then now when we integrate, we would use our reverse power rule. So this would become x to the 0 over 0 plus c. But hopefully right away you're recognizing a big red flag there. We're dividing by 0. And hopefully we all know, of course, that that is not okay. So the reverse power rule for integrals only works when you are not dealing with x to the negative first power. But some of you might also recognize, though, that 1 over x is the derivative of a function that you've learned before. More specifically, you might remember that the derivative of the natural log of x gives you 1 over x. So that means the integral of 1 over x should bring us back to the natural log. And that's why the reverse power rule doesn't work, because it actually turns out to be a completely different function. So let's go ahead and summarize that. So the rule that we're working with today is that the integral of 1 over u du, and by the way, the reason I'm using u is just because most often this particular rule is going to be the result of using a u substitution. So it's much more likely that you're going to encounter this as a 1 over u as opposed to a 1 over x. But again, it's just a variable. It doesn't really matter. This could have said 1 over p for all we know. Okay, so the integral of 1 over u du, it does take us back to the natural log of u plus c. However, there's one trick here. I guess trick's not the right word. 1 over u as a function, think about the only domain restriction we have for 1 over u. And in that situation, u just cannot equal 0. And the thing is with integrals is that the domain from the integrand has to carry over to the actual antiderivative. And if you recall from previous courses, remember that the natural log function, the domain is actually u is greater than 0. So we actually have a little issue here because right now in the original integrand, u could be, the value of u could be a negative value, but that negative value can't currently carry over to natural log of u because then you'd be trying to take the natural log of a negative value, and you're not allowed to do that. So how do we fix that? We just make sure that we take the absolute value of u. So it is important for you to make sure that you remember that the integral of 1 over u du is the natural log of the absolute value of u. And that's how we ensure that the domain from the original integrand does carry over to the actual antiderivative. Because now the domain is u just cannot equal 0. All right, so again, this is the rule that we're using today. And you're going to see a variety of examples here, some of them a little bit more straightforward than others, and a couple of them just getting a little bit more tricky. Okay, so let's go ahead and look at some examples. Okay, so our first example here, we're going to integrate the integral of x over x squared plus 3 dx. So hopefully when you look at that, you realize pretty quickly that this is not a basic antiderivative, so we are going to need to use some sort of a u substitution. Now, I don't have a radical, I don't have a trig function where I have an argument, I don't even have parentheses with a power. So unlike some of the functions that you were integrating in lesson 5-4, this is not necessarily one where you maybe have something jumping out at you initially. However, we do have a couple of things we can think about. One is, I do have a fraction. And remember that in lesson 5-4, one of my tips for choosing a u is to consider using maybe an entire numerator or an entire denominator as your u. Another tip that I gave you was to look for an expression that was that had an exponent 1 degree higher than another expression. And so x to the second is 1 degree higher than x to the first. And you would want to let u equal the expression with the higher power. So all of those tips would seem to point to letting u equal the denominator here. So let's let u equal x squared plus 3, and that would make du equal 2x dx, or in other words, dx equals du over 2x. So now when we substitute, we're going to have x over, and then now x squared plus 3 gets replaced with a u, and then dx gets replaced by du over 2x. And now we can see that those x's divide out, and this integral now becomes the integral of 1/2 times 1 over u du. Hopefully you're okay with that 1/2. All that I basically did was I just treated this as a 1/2. Remember, when the x is divided out, I do still have a 1 in that numerator. And then I can even make this easier on myself and make the 1/2 come out in front. And so now you can see that we have the basic integral for logs. So this now turns into 1/2 times the natural log of u plus c. And then finally we can replace our u with its original expression, which was x squared plus 3. And there you have it. Okay, now, this answer is fine. I have no problems with this answer. However, I would like you at least to try to consider this further analysis that I'm about to talk about. Remember why the absolute value was necessary. It's because we needed to make sure that for no value of x, or u in this case, that we were never trying to take the natural log of a negative value. But think about x squared plus 3. Once you square something, it will never be smaller than 0. And then if you add 3 to that, x squared plus 3 will never be smaller than positive 3. So there is no chance for x squared plus 3 to actually ever be negative or 0. So in this particular example, the absolute value is actually unnecessary. So while this answer is good, or good enough, we could rewrite this then as 1/2 times the natural log of just x squared plus 3 without the absolute value, because, again, we are never going to be taking the natural log of 0 or a negative number with x squared plus 3. And then, if you think about your log properties, remember that the constant multiplying in front can move up as the power on the argument. So this is really the natural log of x squared plus 3 to the 1/2, better known as natural log of the square root of x squared plus 3 plus c. So these are some different answer choices that you could use. Okay? And again, this isn't something that you can always do. You can't always remove the absolute value bars. But this is something that I would like you to at least consider. And I think it's something that's good practice mathematically for us to consider, why do we need to have those absolute value bars? Are they necessary in this particular instance? Okay? And for this particular example, they weren't. All right, let's do another example. Okay, this time we have the integral of tangent of x dx. And some of you might be thinking for just a moment, wait, isn't that secant squared? No, that's the derivative of tangent. We're trying to go the opposite way. And if you recall, there was no trig function whose derivative equals tangent. Remember, we're trying to go backwards. So this is not considered a basic antiderivative because this is not the result of taking the derivative of a trig function. So what do we do here? Well, remember that tangent is really sine of x over cosine of x. So why is that useful? Well, now I can consider using a substitution. Now, this is like what I was talking about a few days ago, where we actually have a couple of potential choices for a u, but one of them is going to actually be useful, while the other one's going to give you a dead end. And thinking about the form that we're talking about today, thinking about trying to get to a 1 over u, it seems that it would make sense to try to let u equal our denominator here. So let's let u equal the cosine of x. And that would make du equal negative sine of x dx. Or in other words, dx equals du over the negative sine of x. So now when we substitute, we're going to get sine of x over u times, and then our dx becomes du over negative sine of x. So now those sine of x's cancel out. I do still have a negative that I'm going to move out in front. So this now becomes a negative integral of 1 over u du. So once again, this is going to become negative natural log of the absolute value of u plus c. And then we can substitute back in for u, and I get negative natural log of the absolute value of cosine of x plus c. Now thinking back to the discussion that I had at the end of the previous example, remember whether or not the absolute value bars are necessary. Thinking about cosine, remember cosine of x ranges from -1 at its lowest to +1 at its highest. So cosine of x does in fact take on negative values or even a value of 0 at some places. So for this particular example, the absolute value bars are necessary. Now some of you might be thinking though, what about when cosine is 0? Remember that can't happen, because if cosine is 0, then that means tangent was undefined anyway. Okay. All right. Let's move on. Okay, so this example is going to be the one that's going to probably give you the biggest headache, so let's just kind of get this out of the way. So similar to the previous examples, we have a fraction here, so x squared minus 3x plus 2 all over x plus 1 that we're trying to integrate. But unlike the previous examples, remember if I'm trying to use the tips we were thinking about before, it would make more sense to let u equal the numerator because that's where we have the higher power. But then the problem is that means we're going to end up having some stuff, some leftover x's in the denominator. It's just not what we want it to be. Anytime you have a rational expression where the degree in the numerator is higher than the degree in the denominator, you're going to want to take the approach that I'm showing you in this example. And that approach is to use long division to rewrite this quotient in an expanded form. And so long division is not going to be probably a lot of your favorite things to do, but it is what it is. So let's just review that quickly. And we get x squared minus 3x plus 2 right there. So remember with long division, we're looking at the first term and multiplying something to get that first term. So x times what gives me x squared, and that's going to be another x. So that's going to be x squared plus x, and then remember we subtract. Those x squares go away. Negative 3x minus x gives me a negative 4x, and I bring down the plus 2, and then we rinse and repeat. X times what gives me negative 4x, and that's going to be negative 4. And then now when I multiply, I have x times negative 4 is negative 4x. 1 times negative 4 is negative 4, but we're subtracting. So those cancel out, and then 2 minus a negative 4 gives me a remainder of 6. And that remainder we write as plus 6 over the divisor x plus 1. So this original problem actually gets rewritten as the integral of x minus 4 plus 6 over x plus 1 dx. Now, how is that any better? Well, because now I can treat this as the integral of x minus 4 dx, so notice how I grouped the first two terms, plus the integral of 6 over x plus 1 dx. So why would I split it up that way? Well, because the first two terms, we can integrate those just using our basic reverse power rule. So that's just going to become x squared over 2 minus 4x. Now, I don't have to put the plus c yet because we still have a little bit more to integrate. The plus c will come out from that last part. And then plus. Now, for here, we need a substitution. So now I'm going to let u equal x plus 1, that denominator. So du simply equals dx. And this becomes the integral of 6 over u du. And so really, this is just 6 times a 1 over u. So now we have x squared over 2 minus 4x plus, this is now just going to be 6 times the natural log of the absolute value of u plus c. And then we can substitute back in. So now we get x squared over 2 minus 4x plus 6 times the natural log of the absolute value of x plus 1 plus c. And then that's basically our answer. And again, question, do we need the absolute value bars here? Yes, x plus 1 can take on values of 0 or negative, so we do need the absolute value here. All right, so in a situation where you've got the integral of a rational function where the numerator has a higher degree, you're going to need to use long division to go ahead and expand or rewrite that quotient in this form, in this quotient form, where you've just got your remainder as a fraction, because then that's the part where we can use our natural log antiderivative. All right, let's just do one more here. And this isn't trying to introduce anything new, it's just one more problem, just so you can see the process one more time. Okay, so we have the integral of sine of t over 1 minus cosine of t dt. And again, hopefully when you look at this, it's very clear that this is not considered a basic integral, so we do need to use some sort of a substitution. So at this point, hopefully your gut instinct is telling you, let's try letting u equal the denominator. So let's do that. So u equals 1 minus cosine of t, so that would make our du equal, so the derivative of 1 is 0, the derivative of negative cosine of t just becomes positive sine of t dt. So dt becomes du over sine of t. So now when we rewrite this, we have the integral of the sine of t over u times du over sine of t. And of course, those sine of t's do cancel out. And now we've got the integral of just 1 over u du. And so that's now just going to become the natural log of the absolute value of u plus c, which we can finally write as the natural log of the absolute value of 1 minus cosine of t plus c. Okay, now once again, do we need the absolute value bars there? Well, remember, cosine would have the greatest value of 1, so 1 minus 1 would be 0. But remember, cosine can't equal 1 because that would actually give us a 0 in the denominator of the original function. But the lowest value that cosine of t would have is negative 1. And 1 minus a negative 1 is actually positive 2. So in other words, 1 minus cosine of t is never going to be 0 or negative. So this situation, 1 minus cosine of t, is always going to be positive. So for this problem, the absolute value bars are actually unnecessary. Okay, and so that is the natural log as it's pertaining to integrals. Now, just as a wrap-up here, though, I want to make sure that we're clear about something. If I have the following problem, now that you've learned about the integral of 1 over u, it's going to be sort of fresh on your brain, and the problem is it's going to make you feel tempted to apply that integral in places where it doesn't actually apply. So I wanted to just review with this particular example. So I'm hoping that if we were to rewrite this, we would notice that this is x over 9 minus x squared to the 1/2 dx. And so our u would obviously be 9 minus x squared. So our du would be negative 2x dx, or our dx becomes du over negative 2x. So now when we substitute, we would have x over u to the 1/2, and then that's going to be du over negative 2x. Those x's, of course, cancel out. I can move the negative 1/2 out in front, and we get that. And the problem is, because you're now thinking about the natural log, a lot of you are going to be tempted to say that this integral right here is the natural log of the absolute value of u to the 1/2. And that is absolutely not true. Remember that it's specifically 1 over u to the first that would give you the natural log of u. If it's 1 over u to any other power, this is just a reverse power rule. So this is where we would have to rewrite it the way that you learned about a week ago. And this would now be u to the 1/2 divided by 1/2 plus c. And then this is going to become, let's see, those 1/2s cancel, and we get negative square root of u, which was 9 minus x squared, plus c. So again, be very careful about trying to overuse or overgeneralize when you can use this particular integral. It only applies when you have 1 over u to the first. So just be very careful about that. Okay? All right. Good luck.